Okay, so previously we've talked about initial yield surfaces, and we focused a lot on von Mises and Tresca. And then we also talked a little bit about um, yield criterion and yield functions that were dependent on hydrostatic stresses, like the Mohr-Coulomb criteria, the Drucker-Prager criteria, etc. So what we want to select now is we want to talk about what happens after initial yield, right? How do we represent those functions if they're changing as a function of plastic deformation? Okay, so let's say we now select. We're gonna select von Mises as sort of our benchmark to walk through this. We could walk through this with other yield criterion as well, or yield functions, but I think to highlight what we're trying to accomplish here, we're just going to use von Mises as our example. Okay, so let's start by just saying we select von Mises as an example criterion. As an example criterion to illustrate subsequent yield surfaces. Okay? So let me remind you what von Mises looked like. We said that was just the yield function f was equal to J2 minus some value k naught squared. And we'll go ahead and we can call that equation 1. This is von Mises. Okay? Hopefully that's straightforward. So now if we ask the question, what happens, after that initial yield point is reached and we continue to load, we cause plasticity. We actually are going to talk, at least in this lecture, about two different models for that sort of have evolved over time. Okay, so subsequent yield surfaces. So subsequent yield surfaces are typically described by by one of two models. Okay, so described by one of two models. Okay, and obviously I could also combine these models. Like we could come up with all kinds of things, but I think as you'll see, one of the challenges is once you define even these very simple models, there's a whole nother set of assumptions you have to go through in terms of how does the yield surface move. And so it's not quite so trivial to just, I guess, maybe introduce evolution equations of arbitrary complexity. But we've talked about these two models briefly before. One would be isotropic hardening, which I hope you're becoming familiar with now. And then kinematic hardening. Okay? Those are our two choices. It is possible, and we'll talk kind of at the end of the plasticity section about how to combine these, but these are the classes of hardening behavior that we typically think of. So let's first talk about isotropic hardening. So isotropic hardening. And again, some of this is going to be a review from when we talked about the 1D case. So hardening. Okay. Let's talk about what this is typically used for. It's often good for. Well, it's actually often used for most metals, and it's not a bad approximation, that are going to be subject to monotonic loading and small plastic strains. So let's just say it's good for most metals. Okay, subject to monotonic loading. That's not cyclic, right? So monotonic loading. Okay, and small plastic strains. Okay, so oftentimes this is just a good choice because it's easy to understand, easy to explain. Okay, small plastic strains. So what are the assumptions that go into isotropic hardening? So let's talk about that. Assumptions. Okay, and hopefully you remember this a little bit from last time. The first assumption is that the shape of the yield surface does not change. Okay, so the shape of the yield surface does not change. Okay, so depending on how we're viewing it, right? If we're looking down on the orthotropic, not orthotropic. If we're looking down on the octahedral plane, then it looks like a circle, right? And it always looks like a circle. We can, in the case of isotropic hardening, we're going to let that circle expand, but we're not going to let it shift. We're not going to let it become not a circle. If you're looking at it in, let's say, a 2D stress space, it looks like an ellipse. We're going to make it continue to look like an ellipse. Okay, so that's assumption 1. Assumption number 2. The yield surface does not shift with respect to the origin. So the yield surface does not shift with respect to the origin. I'm going to say with respect to is just WRT. It's with respect to the origin. Okay. Number 3. The yield surface only expands. Okay, so we don't allow contraction. We don't allow it to shift. It just can continue to grow. Okay? Okay, since the yield surface from the above equation really was just governed by k0 squared, right? That's what told us the outer boundary. We could just replace that k0 value with some new value that governs that outer boundary, right? So let me write that down. So since the yield surface in equation 1, which I had above, is completely controlled by k0, so completely controlled by k0 or k0 squared, we can simply write the subsequent surfaces. So write the subsequent surfaces as follows. We can say that now F is equal to J2, I'm going to say now minus J2 bar. Okay? We'll call that equation 2. Where, let me just define this, right? Where J2 bar is equal to K0 squared initially, right? And it's just some value, and that value grows. So it can change. So it's k0 squared initially, but can change, or but will change with increasing plastic strain. So we could write something like the increment, let's say dj2 bar, is a function of the plastic strain increment, for example. Okay? We can call that equation 3. Okay, so one thing I want to say then is that what does J2 bar really represent? Well, it really represents an internal state variable, right? So let's just note that in this way, J2 bar represents an internal state variable. Okay? Right, we defined those previously, but it represents the internal state variable, and it's going to control the plastic strain for isotropic hardening. Right? So it's a single variable. So then our internal state vector, remember we represented that as Q. So internal state vector Q is just going to be equal to single value Q1, which is going to be equal to J2 bar. Right? That's one of our only internal variable here. Okay. One thing I want to point out, so just note this. So note right? The equation 2 that I wrote above, let's see if I can scroll up so you can see a little bit better. Right there, right? Equation 2 that I wrote up there, it gives us the form for some subsequent yield function for isotropic hardening, but it doesn't tell us how J2 bar is going to evolve with plastic strain. Okay, so equation 2 gives the yield function for subsequent yield surfaces. Okay, but does not tell us how J2 bar evolves with plastic strain. Okay, so how do we get that? Well, we actually have to look at some sort of calibration curve to see what that looks like. So maybe you have a uniaxial stress-strain curve where you can identify the onset of yielding and also the hardening behavior. Then you would be able to back out how J2 bar will evolve with plastic strain. Okay, so that's isotropic hardening. That's the easy one. Now let's talk a little bit about kinematic hardening. Okay, so we can write kinematic hardening. Okay. When is this important? Well, it's important to think, at least consider using kinematic hardening if we're going to do anything that involves cyclic loading or load reversals. So potentially important for cyclic loading and or that's supposed to be or load reversals. Okay. What assumptions do we have for kinematic hardening? So here's our assumptions. Right. Number one, the yield surface only translates in stress space. So yield surface only translates in stress space. Okay, that means that the yield surface has a constant shape, size, and orientation. Okay? So what does that mean? That means that we need to locate the center of the yield surface in space. So that's what's needed to describe this. Right, so we need to locate the center of the yield surface in space. Okay? How do we do this? So we introduce a backstress tensor, right? Backstress tensor that we call alpha. That gives the center of the yield surface. I'm going to put center in quotes because it doesn't have to be symmetric or whatever, but it locates the origin, okay, of the yield surface. Okay, so a couple things. First, note that the form we had for the von Mises doesn't readily admit this sort of shift. Okay, so note that our, let's say, previous form for f, the yield function, right? So that was equation 2, doesn't easily accommodate this. Okay? Right, so remember this was that equation 2, I'm going to write it again for you, was just that we said that J2, this is the initial yield surface, minus K naught squared is equal to the yield function. Well, this J2, that's a scalar invariant, right? Okay, that's not so easy to see how we can shift our yield surface using a scalar quantity. So let's try to write this a little bit more generally now. So let me just see if we can recall what we talked about before. In generally, for any yield surface, so generally we have that F is equal to some function of sigma, the stress, and our internal variables Q, which at least up above so far, we would just write that would be F sigma and K naught, right? Because we can use sigma to get to J2. And what we want to do is we want to shift this by alpha, right? That's the backstress. So we could write that as, if we were writing this as a shift, that F is equal to, let's say, sigma minus alpha K naught. And of course, the surface is where this equals 0. Okay? So this is our shifted surface. We can call this equation 5. Okay, so what about the case of the von Mises yield criterion? So let's look at that. So in the case of von Mises, a yield surface, then what does equation 5 become? Well, equation 5 becomes the following. It says F is equal to, well, what is J2? You remember what J2 looked like? It was 1/2 times Sij, Sij, where, remember, Sij is the deviatoric stress. So it really ends up being 1/2 times Sij minus alpha ij, shifted, times Sij minus alpha ij, right? Minus K naught, the quantity squared. We can call that equation 6. Okay, so this will be our yield function for the case of kinematic hardening. So this is how we would write that. Okay. So now if you're like me, you're thinking, well, that sounds great, but I went from having in an isotropic case, I had a single constant or single scalar quantity I had to compute, and I think I understood how I would do that with respect to, let's say, a uniaxial stress strain curve. Now I'm looking at this and I'm seeing, well, I guess in theory, even if we assume that alpha is symmetric, I see at least maybe 6 quantities I have to evolve in order to capture kinematic hardening. Maybe I want to go to principal stress space, and so I could say I maybe only need to evolve 3 in principal stress space. But still, it's a significant amount more work than the isotropic case. And you'd be right. This is a significantly more complex hardening approach. Okay, so I want to make a couple comments about that. But the primary one is that the manner in which the backstress tensor alpha evolves is kind of a subject unto itself. So there's lots of different approaches that people have taken to do that. We're not going to delve into them now. I just want to make you aware that if you don't just automatically see how we would do it, that's to be expected. You're going to have to make some assumptions. So let's write that down. The manner in which the backstress alpha evolves is a subject unto itself. Okay, that's not to say that there's not good work out there that helps us with that, but it's not just trivial and it's not just obvious. I'll just say that the simplest approach is going to come from a gentleman that you have heard before, but the simplest approach was from Prager, is what's called Prager's linear kinematic hardening, which states that d alpha ij, the increment in the backstress tensor. Remember that alpha ij begins at 0 because that's where your yield surface is centered. But d alpha ij is going to be in the direction, let's see, so it's going to be in the direction that's given by this partial F with respect to sigma ij. Right? So if you remember that, that's going to be in the direction that the plastic strain is incremented. Okay? So if you have that, then you can say, so the d alpha ij is in the direction given by the partial F with respect to sigma ij, and this only requires then computing some proportionality constant. Okay? And that proportionality constant is actually the plastic tangent modulus. Okay, I'm not going to go into how to do that. I will post some papers rather that go through this in more detail. But the idea being that if we just pick the direction, then we can develop a theory for how it might stretch, how it might shift in that direction as we increment plastic strain, and we can calibrate that with a single curve. I want to make one final remark in this lecture, and it's not really related to either isotropic or kinematic hardening. Okay. It's sort of a consequence of some of our assumptions about yield criterion. So if we assume that plastic deformation doesn't occur in response to hydrostatic stress, right? I think we've hopefully covered that in gory detail, right? Both from a mechanistic perspective, we know that at least dislocations don't glide in response to a hydrostatic stress. So the plastic deformation is not going to accommodate or move to accommodate a hydrostatic stress. So that has an implication. Okay, so let's just say if we assume that plastic deformation doesn't occur, plastic deformation does not occur in response to a hydrostatic stress, and which is the assumption, for example, in von Mises or Tresca, right? What that means is that plastic deformation is volume conserving. And why is that? Because the deviatoric component of the stress can only shape change. It can't change volume. And the hydrostatic is what is the dilatational component, as it's called, which either can compress or expand the volume. So is volume conserving. Okay? So plastic deformation has got to be volume conserving if it's not responding to a hydrostatic stress. That has an implication as well, in that for an isotropic material, you need a Poisson's ratio of 0.5 for plastic strains. Okay? So obviously elastic strains can still do what they would like to with respect to the Poisson's ratio, but plastic strains must retain a Poisson's ratio, if you like, of 0.5, and you can go convince yourself just with a simple prismatic tension test that a nu of 0.5 is what gives you a volume conserving response for at least an elastic material. So just wanted to make you aware of that, remind you that that's one of the outcomes of making the assumption that plasticity only occurs in response to deviatoric stresses. Okay?